Hey, welcome! Today we're diving into a huge scientific mystery, something that puzzled some of the greatest minds for centuries. And it's all about this simple fact: the solid ground you're on right now, it's actually moving. We're going to piece together the incredible story of our restless planet. You know, it all kicks off with a really simple observation, one you've probably made yourself. Have you ever just stared at a map and noticed how the coast of South America seems to fit almost perfectly into the coast of Africa? It's uncanny, right? Well, that one little question is the key that unlocked this entire epic story. So our investigation starts more than 100 years ago, with a scientist who had the guts to suggest that maybe, just maybe, the continents weren't stuck in place. His name was Alfred Wegener, and he was the very first person to really try and put this giant global puzzle together.
Okay, so back in 1915, Wegener rolled out his Continental Drift theory. He said that the continents we know today were all once connected in this massive supercontinent that eventually broke apart. A brilliant idea. But there was a huge problem. When people asked him how they moved, his best guesses were things like tides or the Earth's rotation, which, as other scientists quickly pointed out, were nowhere near powerful enough. His idea was incredible, but without an engine to drive it, the scientific community pretty much laughed him out of the room. But Wegener, he had clues they just couldn't ignore.
Yeah, Wegener had collected some seriously convincing evidence. I mean, think about it. He found the exact same fossils of land animals on continents that are now separated by thousands of miles of ocean. He was able to match up rock formations and whole mountain ranges across the Atlantic like they were torn from the same piece of paper. He even found evidence of ancient glaciers in places that are now scorching hot tropics. He knew something was up, even if he couldn't explain the how. So for decades, Wegener's idea just sat there. The case went cold. Then, around the middle of the 20th century, new technology finally let us explore one of the last great frontiers on our own planet, the bottom of the ocean. And what we discovered down there, well, it changed absolutely everything. Down in the deep, scientists found these gigantic underwater mountain ranges called mid-ocean ridges. Building on some earlier work, a guy named Harry Hess came up with this revolutionary idea: seafloor spreading. He figured out that hot, molten rock from the Earth's mantle was bubbling up at these ridges, creating brand new ocean floor, and then pushing the old floor outwards. Think of it like a giant conveyor belt, constantly making new ground in the middle and pushing the old stuff away. This was the powerful engine that Wegener's theory had been missing all along. So, with that last critical piece of evidence pulled from the depths of the sea, the puzzle was finally complete. Continental drift and seafloor spreading snapped together to create one of the most important, most unifying theories in all of science. So by 1967, this new, complete understanding got its official name: the theory of plate tectonics. And the name actually comes from the Greek word for to build, which is just perfect. The theory basically says that the Earth's hard outer shell, the lithosphere, isn't one solid piece. No, it's shattered into these massive plates. And these plates, which carry both the continents and the ocean floors, are kind of floating and sliding around on a hotter, softer layer right below it. And what's so cool about this slide is how you can actually see the scientific journey laid out. You see how we started with a discarded idea that was only about continents, then we moved to an incomplete idea that was only about the ocean floor, until we finally landed on the big one, plate tectonics, which explains the movement of everything, continents and oceans, all powered by that same incredible engine in the Earth's mantle. Okay, so if these enormous plates are always on the move, what happens when they run into each other? Well, that's where all the action is. The edges, the boundaries between the plates, that's where mountains get built, where volcanoes blow their tops, and where earthquakes shake the ground. And they interact in three main ways. First up, you've got divergent boundaries. This is where plates are pulling apart from each other. Hot magma rises up from below and creates new crust. That's seafloor spreading in action. Then you have the opposite, convergent boundaries, where plates are moving together, they're colliding. And what happens here is one plate usually gets forced to slide underneath the other. We call that subduction, and it gets recycled back into the mantle. This incredible pressure is what gives us towering mountain ranges and strings of fiery volcanoes. Now, the third type is a transform boundary. Here, plates aren't creating or destroying. Instead, they're just grinding past each other, moving sideways. But the friction is absolutely immense. The plates can get locked together, building up stress for years, decades, even centuries, until they suddenly snap and release all that energy in a violent jerk. The most famous example of this? California's San Andreas Fault. And that sudden, violent release of built-up energy at a plate boundary, well, that's exactly what an earthquake is. Understanding plate tectonics isn't just an abstract idea. It lets us understand why, where, and how these incredibly powerful events happen. And this right here really illustrates the kind of power we're dealing with. The Richter scale isn't like a ruler, it's logarithmic. What that means is a magnitude 6 earthquake isn't just one step up from a 5. It releases about 32 times more energy. And going from a 5 to a 7? That's not 2 steps up, that's 1,000 times more energy. The power just skyrockets.
So where is all this shaking happening? The chart makes it pretty clear. A wild 68%, more than 2/3 of all earthquakes, happen along the Circum-Pacific Belt. You probably know it by its more famous name, the Ring of Fire. It basically lines the edges of the Pacific Ocean, and it's where a ton of different plates are all crashing and grinding against each other. It's a real hotbed for seismic and volcanic activity.
You know, it's so important to remember that this isn't just stuff that happened millions of years ago. The tectonic plates are moving right now. In fact, they're moving at about the same speed your fingernails grow. It sounds slow, but over geologic time, that steady, relentless movement completely redraws the map of our world.
This timeline is the perfect example. Let's look at the journey of the Indian Plate. About 200 million years ago, it broke off from a supercontinent way down south. Then, for over 150 million years, it traveled north across the ocean until it finally, bam, slammed into the Eurasian Plate. That colossal collision, which is still happening, is what created the Himalayas, and it's still pushing them a little bit higher every single year.
So the main takeaway here is that the world map you've always known is really just a snapshot in time. The continents have been doing this slow-motion dance across the face of the globe for billions of years, and they're going to keep on doing it for billions more. Which leaves us with a really fascinating final thought to chew on. What will our world actually look like in the deep, deep future?